Okay, so on Friday we were talking about the laws of thermodynamics. Just to review, the first law of thermodynamics is essentially the law of conservation of energy. Energy can't be created, it can't be destroyed, it can be transferred, okay, by either heat, which would be the transfer of thermal energy, or by work, the transfer of mechanical energy. Okay? Any work that is transferred to a system will either be transferred as mechanical energy or will be converted to other forms, and the same for heat. Okay? If we transfer thermal energy to a system, it'll either gain thermal energy or that thermal energy will be converted into other forms of energy in the system. Okay? It isn't going away, it isn't being created from anywhere, it's always going to be constant. Then we talked about the second law of thermodynamics, which talks about the direction that heat is transferred. Okay? And heat is always transferred from the hot object to the cold object. Okay, that's the second law of thermodynamics. It always flows from hot to cold, and that was the design, or the idea behind the design of this hypothetical, terribly designed boat. Right? The idea was that if one part of the engine was in warm water and the other part of the engine was in cold water, that heat would flow across from warm to cold, and that would of course take water with it, turning the turbine, propelling the boat forward. Works great in theory. In practice, this design is really poor because the warm water near the surface and the cold water near the bottom are already in contact with each other. Okay? There's really not a lot of motivation for it to travel the turbine.
What if?
What if? I like what if. Okay?
So you take a solar panel to use an electric stove to heat up a pot of boiling water, and then you put the boiling water into the hot water. So then it transfers to the cold. So you're using the sun to heat up water to turn the turbine.
Yes. The issue is that solar power is incredibly low. Okay, I mean, we like to think solar power is great for powering things, but you have to have so much solar power to generate anything. Like, for example, if you have a 100-watt solar panel, okay, and a 100-watt solar panel would be about half the size of the smartphone, okay, that length and about half the height, okay, that will generate about, so it'll generate 100 watts per hour, sorry, 100 watts, so that's 100 joules per second. That's if it's running at peak efficiency. That electricity then goes through to an inverter, which converts it from direct current to alternating current so that you can boil your water. That loses at least half of the energy right there. So it's really hard to actually run anything off an alternating current from a solar panel unless you have a lot of solar panels. They just don't generate a lot of electricity on their own. I know, I have one attached to my trailer, and it'll keep the batteries charged for the most part, but as soon as I plug anything into the inverter, the batteries go away. So they're good for maintaining. They're good so you don't have to run a generator necessarily, but on their own, you need a lot of them. And you need to be in a really sunny place. Okay. Heat engines. Okay, so we talked about the heat engine. The heat engine uses the second law of thermodynamics. Okay, it harnesses the fact that energy, or heat, thermal energy in particular, wants to travel from hot to cold. If we can put something between the hot and the cold, we can make it turn because matter is going to flow with the energy, okay, causing that turbine or whatever it is to turn. And that's exactly what a jet engine is. Okay, a jet engine is a heat engine. That is why it is a big giant turbine. So the place where we burn the fuel is obviously very hot, okay? And it is forward of the turbine. As that heat travels from the hot area across the turbine towards colder air at the back of the engine, okay, the turbine is turned, and that produces thrust. Okay? The more fuel we put in, the greater the heat differential, the greater the thrust that is produced. If we don't put in a lot of fuel, then we don't get a lot of thrust. Everyone kind of follow me on that? Okay, so the bigger the energy difference, the faster the heat will flow, okay, and the faster the turbine will turn. Now, there's also a way to make this work in reverse. Okay? It's called a heat pump. We call them more typically refrigerators and air conditioners. Okay? Refrigerators and air conditioners are heat pumps. What they do is they take heat from a cold area and force it into a hot area against the second law of thermodynamics. Now, you might think, wait, Mr. Cooder, you're just saying that you can break the laws of physics. I'm not saying you can break the laws of physics. You can get around them. Okay? Unfortunately, it's kind of like real life. You get around the law if you got enough money. True, unfortunately. Okay? At least we see it all the time. But the same is true for thermodynamics. If you've got enough energy, you can get around the second law of thermodynamics by expending energy to pump heat from a cold area to a hot area. In the same way that you can make water go uphill, provided you use energy. Right? If I want to make water go uphill, I have to have a pump, and a pump uses energy. Okay? It's not going to go uphill on its own. Okay? Well, heat's not going to come out of your food, okay, and into a warmer room on its own. Everything wants to go towards the refrigerator because the refrigerator is the cold area. Okay? That's the way it wants to go. So what happens in an air conditioner or a refrigerator is we use a coolant. Okay? And we'll get there in just a minute. Sorry, I should talk about the heat engines first. Got out of order here. Okay, so this is, you know what, I'm going to talk about heat pumps, and I'm going to come back here and talk about the straight. Okay, so in your refrigerator, when it's running, you can hear it, right? It makes all that noise. That's the compressor. Okay? The noise you hear when your fridge is running is the compressor and a fan. Right? What happens in your fridge is there are pipes through the walls and ceiling of the refrigerator. Running through those pipes is a coolant, okay, or a refrigerant. It is a gas when it's under certain conditions. Okay? So as it runs through those pipes in your fridge, it's a liquid. As it absorbs heat from the food inside your fridge, it changes state from liquid to gas. And then it goes back to the compressor. And the compressor puts pressure on it. When you put pressure on a gas, you can force it back into a liquid state. When you do that, energy is released. All the energy that the coolant absorbed from inside the fridge, okay, is now released by the compressor. That's why you have a fan, and sometimes if you stand in front of your fridge, you can feel that warm air coming out from underneath. That's the fridge venting the heat, pumping the heat into a hotter area from inside the fridge. Okay, that sort of makes sense? So it's allowing this coolant to absorb energy and change state, running it to a compressor, which then recompresses it down back into a liquid, okay, and then that heat gets pushed out into the surrounding area, okay, that is warm. So it goes against the laws of thermodynamics, but it uses energy to do it. In fact, your refrigerator is probably the largest consumer of electricity in your home. Okay, unless you use like electricity to heat something. Okay, if you have an electric hot water tank, it might be on par with your refrigerator. Okay, if you have an air conditioner in the summertime, it's probably going to use more energy than your fridge. Okay, but most of the time, your fridge uses more electricity than anything else because this process, going against the second law of thermodynamics, takes a lot of energy. Right? And it's similar if you're running an air conditioner in the summertime. Right? What's happening is, okay, air from inside the house is being pushed over coils, just like what are in your fridge, except there's way more of them in the air conditioner, okay, being run over these coils, okay, and those coils have the same kind of refrigerant in them. That refrigerant turns from liquid to gas, goes to the compressor recompresses it, and pushes the heat back out to outside, which can be significantly warmer than inside. Okay? And so that takes a lot of energy. Right? Next summer, when your air conditioner is running, just stand next to it. You can feel the heat coming off of it. Right? And if you actually look inside of your air conditioner, don't stick your hand. Can't believe you're sticking it. Okay? But you can see inside, right in the middle, there's just like looks like a big kind of oval piece of metal. Okay? That's the compressor, full of the coolant and turning it back into a liquid. Okay? There's a lot of space around it. There's the coils around that, and then there's a fan on the top that's blowing the air that's hot out of it and into the surroundings. It's pumping the heat from the cold area to the warm area. Okay? That takes a lot of energy to do that. Everyone okay with that idea? That's how a heat pump works. Okay? So the process is not natural. So work must be done by the refrigerator. Okay? Energy has to be used to pump refrigerant through the copper piping. Okay? So that thermal energy is transferred to the air surrounding the refrigerator, and then the refrigerant is pumped into the condenser or compressor where it's cooled and liquefied, and then the cycle repeats. Okay? It's the same for your air conditioner. All right. So if we go back to looking at this heat pump, heat engine. If we have really, really hot water and really, really cold water, okay, we can use a thermocouple to run this fan. Okay, so initially when the water is really hot and this water is really cold, okay, the fan will spin really, really fast. But as these two things start to equalize, what's going to happen to the speed of the fans? Yeah, it'll just keep getting slower and slower and slower and slower until the energy differential is gone and then it'll stop. Okay, everybody all right with that? So this actually works. Like, if you had a thermocouple like this, we actually make that work. Okay. All right. Now, again, the big thing here is the bigger the difference, the faster that fan is going to spin, because the more easily the heat will transfer. Okay. I would like you guys to answer those questions there about the laws of thermodynamics. So, okay, when it's saying state the laws, try and put it in your own words rather than copying what's in the notes. Read what's in the notes, but try and put it in your own words. It'll be a little more meaningful that way. Okay, give you a few minutes on that and then we'll talk about those. Okay, so first law of thermodynamics. Okay, energy can't be created, it can't be destroyed, but you also need to have in there something about what happens to energy when it is transferred. Okay, so we got something about work and something about heat in that definition, because if you look back in the notes, they also talk about work and heat in their definition. So if work is done to a system, its energy will increase. Okay, if heat is transferred to a system, its energy will increase, and then vice versa. Okay, if a system transfers heat away, it loses energy. Okay, if it does work on something, it loses energy. It's not creating it, it's not destroying it, but it's turning it into other forms and transferring it away. All right, distinction between work and heat. Work transfers what kind of energy? So, mechanical. Okay, and heat transfers thermal. So they're both transfers of energy, but they transfer different types of energy. Okay, identify whether each of the following is best explained by the first or second law of thermodynamics. A bouncing ball eventually comes to rest on the floor. Second. Which has more energy, the ball or the floor? The ball. The ball is moving. The floor doesn't have any energy. Okay? As the ball is moving, it's turning its mechanical energy into sound, heat, transferring it away. It's flowing from the hot object to the cold object. You could make an argument for the first law as well, okay, in that we're talking about transfers of energy. So both could really work there. Okay? A metal spoon eventually becomes hot when placed in a pot of boiling water. Also, by the way, don't stir something that's going to be on the stove for a long time with a metal spoon, because this will happen because of the second law of thermodynamics. Okay? Energy goes from hot to cold. Okay. Energy cannot be created or destroyed. Sounds familiar? First law. Okay. Question number 7. State the second law of thermodynamics. Energy flows from hot to cold. That's really what I need to say. Okay, number 9, water is observed to condense on the outside of a cold glass. Which way is energy transferring? From outside to inside. It is transferring from the air to the glass. The glass is colder. The energy can't be going from the glass to the air. Right? It's the second law of thermodynamics. Now, why is there water condensing on the glass?
The water vapor in the air, when it pushes the air is going towards the glass, so it's from hot to cold, and it condenses because it's going to not as cold, and it freezes, not freezes, it's colder.
And condenses, right? Okay. So water vapor in the air has lots of energy because it's in the form of a gas. When it comes into contact with the cold surface of the glass, it loses energy, so much so that its temperature drops to whatever, to 100 degrees or whatever, okay? And it transfers its thermal energy from the air to the glass, and it condenses down to the liquid form. Right? So that's what we see there. In fact, that is one of the reasons why steam at 100 degrees burns you far worse than water at 100 degrees. Okay? Because steam at 100 degrees has changed state into a gas, and that requires a ton of thermal energy. So it has the same amount of kinetic thermal energy, as water because they're both 100 degrees. But it has way more potential thermal because its particles, okay, like a liquid, the particles would be about this far apart, but in a gas, they're this far apart. Okay? And when the gas condenses back into a liquid, the particles move closer together and release huge amounts of energy in doing so. All right? So always stay away from hot steam, okay? Because it will burn you far worse than water of a similar, the same temperature, both 100 degrees. Okay? It's also why pressure cookers are so dangerous. Okay? Inside a pressure cooker, you can get liquid water to be hotter than 100 degrees. Okay? So as a result, if it breaks open, it will rapidly vaporize and then recondense, releasing lots of energy. Okay. Number 10, which law of thermodynamics best describes the following statements? Explain your answer. You can't get something for nothing. First law, yeah. Energy can't be created and it can't be destroyed. If it can't be created, you can't get something for nothing. Okay, it's also why perpetual motion machines won't work. You can't even get close. Still first law, still, okay. You can't get something for nothing. In fact, you can't even get close to getting something for nothing. All right, a rock will never suddenly jump into the air. First law, they're all first law. Okay? If a rock suddenly jumped into the air, it would be because energy was suddenly created and the rock flew off the ground. Okay? All right. Questions on any of those? Did you give those? Okay. All right. Is this one in your own deck? I don't remember if I cut this off or not. I think I did, but I still want to go over it. Okay. So this has to do with development of engines and how that kind of relates to thermodynamics. If there's anything you need to copy, I'll underline. Okay? So don't go copying what's here. All right. So what we have are a few examples of early machines that could do work. Okay, they did mechanical work. Right. So one of the earliest pumps was the Archimedes screw. Okay, it was basically just an auger, but if you turned it fast enough, the polar nature of water would keep the water kind of stuck to this, and if you turned it, the water would pump up the screw and out the top. Now, it didn't work very well in that you could only pump water a couple of feet, okay, because the water would obviously want to run back down the screw all the time. So you had to turn it really fast, and it would only work to raise water, a couple of feet. So it wasn't great, but it did some mechanical work. Okay, the Persian wheel, okay, that was also essentially like a pump. Right? It could be used for like aqueducts and stuff like that. So they would raise water to a certain height, it would fall onto here and then run down, and its potential energy would turn into kinetic energy, and it could turn, like a mill or something like that. Okay? So they were kind of easy, simple pumps. Right? Now, a little more in depth would be a reciprocating pump. Okay? A reciprocating pump is one that can work in both directions. But to do that, you have to be able to seal off the pump chamber after you draw the water in. Okay? So a reciprocating pump works like this. When you pull back on this piston here, it creates a suction. That suction will pull up the intake valve, and it will close this valve. Okay? Everyone kind of follow me there? Right? And so that will draw water in. Then when you start the piston moving back this way, that forces the intake valve closed and pushes the outtake or the outlet valve open, and you're allowed to pump water. Okay? If you don't have these valves, just moving the piston back and forth doesn't do anything because the water tries to come up and then just gets forced back down again. Right? So you have to have these valves that open and close. Okay? Kind of like the walls of a lock. Okay? As you're going along, like the St. Lawrence Seaway, for example, has all these different locks, right? They pump water into them, and that allows the boats to go uphill. All right, so reciprocating pump. Now, the big thing here, guys, with different types of engines, we needed to have engines that work because otherwise we were always relying on the power of people or the power of beasts of burden, okay, cattle, oxen, donkeys, whatever, okay. We were always relying on them as a source of mechanical energy, making them move. That can be inconvenient because people get tired, animals get tired, you have to feed them both, okay? In the case of animals, you have to clean up after them, maybe people too, okay? But you have to have large numbers of people doing a lot of menial, manual labor, all right? It would have been a lot easier to have a machine that could replace the manual part, the mechanical parts, okay? So the idea was that if you were going to build an engine of some kind, you had to have it converting one form of energy into the desired form of energy, right? When it was always people-powered, it was mechanical to mechanical, and you were fine. But if you're making an engine that doesn't require mechanical energy as its input energy, you had to replace that with something. And the most readily available form would be heat. How do you get heat? You burn stuff. Okay? You burn stuff, it gets hot, and then you can use that heat and turn it into mechanical energy. Unfortunately, that's really inefficient. But all of our engine technologies revolved around it. Okay? Until we started developing better electric engines and things like that. So the first idea, and luckily it didn't catch on because it was highly impractical, was the gunpowder engine.
Oh, yes.
Okay? Because we had already invented the rifle. Okay? And we knew that when you made gunpowder explode, there were expanding gases associated with that, and that's what would propel the bullet through the rifle. Okay, so when you, or if it back then probably like a musket. So you would, if you know what I mean by a musket, they would have like this bag full of gunpowder, and they put it in the gun, and then they would jam a ball down the rifle with this big long stick. Okay, and then they would get ready and fire. And then everyone would start it over again. It was really, like, you didn't get a lot of shots off, okay? You got like 2 shots off, and in a minute you were incredibly efficient at loading and reloading your musket. The other problem with muskets is you could fire them out 2, maybe 3 times, and then they were too hot to be safe anymore because you were putting gunpowder into hot metal. Okay, also not very safe. And they had a real tendency to blow up in people's faces. So they weren't really reliable. But we did discover that when you blow up gunpowder, it gets hot and there are expanding gases. So the idea here was that if you could create a chamber that could hold the explosion, and it had a movable piston in it, when the gases expanded, they would push the piston up. That's mechanical energy. If you attach the piston to something, then as the piston moved, the something else would move too, and work would be done. Now, that's all well and good in theory. There's a lot of problems with the gunpowder engine. Like, they'll blow up. And they're really not reciprocating. They go once, and then you have to reset the whole system. Refill it with gunpowder, move this piston back down. It's not going faster by any sense than a beast of burden or a person would do the job. Okay? But it kind of was the precursor to better forms of energy. All right? Now, that, yeah, obviously, so that was Christian Huygens, the same guy that discovered like moons of Saturn and stuff like that. Right? So it was not developed because of the obvious hazards of explosions and because there's no powerful internal mechanism to pull the piston back so the engine could operate continuously. Okay. Then we had this first kind of like heat/steam engine. Okay, and it had like these 2 hemispheres, which I'll show you in a minute. But okay, this was like the first steam-powered engine. It was what we call an external combustion engine, in that the heat source is outside of the engine itself. So you would heat up this big kettle, okay, and the water inside would evaporate, and the steam would take up more space than the water, slowly pushing the piston up. Right? That's great. You get 1 stroke. Okay? The piston moves up. Then what? Then you have to put the fire out, cool off the container so that the gases condense back into water and the piston comes back down. Then you have to start the fire and heat the engine back up. Right? It's not very efficient. Right? You're not getting a lot of strokes per minute, okay, on something like that. Not a lot of RPMs there. Okay? So it's not doing a lot of useful work. Okay? So the Savory engine, okay, was a little bit better. Okay, there were these different. There was your boiler, and then the steam would go from the boiler into the part of the engine that would do the usable work, and then water would come back out. The advantage of this was you didn't put the fire out all the time. Okay, you had steam being piped from the boiler to the part of the engine where the pistons were, and then you could recondense the water. Okay, so the water would come in, go in here, right, and we would have that working a little bit better. Still didn't cycle very well. Okay, the new common engine, okay, was even a little bit better than that. Okay, you had the boiler producing steam that forced the piston up. When the cold water was sprayed on the outside of the cylinder, it would come back down. Okay, so it was easy to build and maintain, could pump water pretty well. Okay, but the cycle of heating and cooling was still really inefficient. All right, so Watt comes along. Okay, Watt builds like basically the first reciprocating steam engine. Okay, so we realized there was a lot of wasted heat when the water was heated and then cooled in the same cylinder. So Watt designed a more efficient steam engine that had a separate condenser to cool the steam so that the boiler cylinder always remained hot. And that reduced the amount of heat required to operate it and made it 3 times more efficient. Okay, and his engine was used for like 100 years. Okay, so it was really a lot better than what they had. Okay, so steam engines, the problem with them is that they were large. They were huge. Okay, they were only going to be useful in like a factory type of situation. They weren't going to be useful for vehicles. Okay, at least the early ones, okay, because they had to be so big. Then, as obviously the technology miniaturized, we were able to use them for locomotives. Okay, so for trains, train engines, and things like that. They still had a lot of problems, mainly being the ability to construct an airtight container. Most of the problems associated with the steam engine were loss of compression due to leaks, okay, at any of the seams where the metal was put together. It's really hard to get these seals really, really tight, okay, which is why lots of times you watch old movies, you see steam escaping from all these different places on a train. Okay, it's just because it was really hard to keep the seals really, really tight. Okay. Okay, so this is kind of the timeline here. Okay, steam engines, like we said, they were big. They were pretty inefficient. So we needed a way to miniaturize them. The way to miniaturize a steam engine, or any engine, was to make it what we call an internal combustion engine. Because steam engines, by definition, are external combustion. Okay? That is, the combustion takes place separate from where the cylinder is. If you can make the expansion of gases take place in the same place where your piston is, then you're going to be more efficient and smaller. Because you don't need the 2 separate parts. Okay, so that's where the internal combustion engine comes along. Okay, so they were powered by different things, and the big problem was getting a fuel that worked really well that didn't gum up the engine. Okay, because there was a lot of reliability issues with the first ones. Okay, so they got these internal combustion engines here using like tar and oil and coal gas and stuff like that. Okay, so internal combustion engine. So Robert Steele, okay, he made up the first internal combustion, and it used coal gas ignited by an electrical spark, which is essentially the same thing we do today, right? Every cylinder in your car's engine has what's called a spark plug. Okay, and on that spark plug, okay, there's an electrical connection to that, and the plug just makes an electric arc that ignites the compressed air-fuel mixture in the cylinder. Okay? So this was an internal combustion engine, meaning energy was released by burning fuel ignited by an electric spark inside the engine, okay, and we still use that today. The drawbacks to it were that it didn't have any sort of really good lubrication, and so the engine would seize easily. Okay, because as the engine would get hot, what would happen to the metal? It would expand, and the piston wouldn't move up and down in the cylinder very well. Okay, when the engine was cool, it didn't create a tight enough seal, and a lot of the compression was lost. Okay, so there was really this kind of happy medium in there that they couldn't really find. So here's your modern, okay, 4-stroke, okay, internal combustion engine. Right? We call it 4 strokes because that's how much it has to go. It has to go through essentially 4 times to make it work. Okay. So here's the first part. The first stroke is like the intake. Okay. So during the intake phase of internal combustion, the piston is moving downwards, and when it does that, it creates a vacuum. Right? You follow what I mean there? Like if you're drawing liquid into like a syringe, right? You pull a plunger. Okay, it creates a vacuum or a suction that draws stuff in. So during the intake phase, the intake valve is open, right? And the cylinder or the piston is moving downwards, and it's sucking in, okay, the air-fuel mixture. Okay. Then on the next phase, the intake valve closes, and the piston begins to move upwards. What's it doing to the air-fuel mixture? Compressing it. That's why this phase is called the compression phase, right? So it's moving upwards, and it is compressing the air-fuel mixture. Then we have the ignition phase, where the spark plug sparks and ignites the now compressed air-fuel mixture. Incidentally, the more you can compress that air-fuel mixture, the hotter the explosion, right? Which is why some cars will run on premium fuel and some won't. Most of the time, a higher compression engine will need premium fuel. Okay, so some engines are designed to have more pressure in them, and as a result, they generate more power. Okay, so during the ignition phase, okay, that spark ignites, and when it ignites, then we get the expansion or the power stroke. Okay, this is the part of the cycle that actually makes mechanical energy. So the expanding gases force the piston down, okay, and that does mechanical work. Okay, then the piston cycles back up, and the exhaust valve opens, and those spent gases now go out through the exhaust valve and into the exhaust system. Your headers, exhaust pipe, muffler, what's that? Or if you have a turbocharged vehicle, yes, there will be a small bypass here that has some of those hot exhaust gases that actually spin the turbo. Okay, that's a bit more complex because the turbo then creates more pressure, and that creates a hotter burning situation. So if you have a turbo, okay, it's using the gases that are spent to increase the pressure at which fuel is pushed into the cylinder. Okay, and that creates again a hotter burning type of fuel. All right, everyone kind of follow how that works? Okay, that's like very, very basic for how an engine works, but that's essentially how it works. Okay, there's all kinds of different things that can go along with that, how the valves work, if they're operated from above or if they're operated from below. All of those can change, okay, how an engine works, but effectively this is it. The piston moves up and down like this, and those strokes. Okay? All right.
Has there ever been a two-stroke engine in a car?
Oh, probably. I mean, motorcycles for a long
Yeah,
time ran on both. Yeah, I would assume probably some of the early ones would have been two-stroke. Yeah. The problem with that is always having to mix the oil in with the fuel, right? And it's really dirty. Like a two-stroke engine is incredibly dirty.
It wears the engine down faster.
Well, it wears the engine down faster, but it's just pollution. It's crazy because you're constantly burning that oil. Right? What's that? From a two-stroke? It depends. It would really depend. Like a lot of older boats used to run on two-stroke diesels, and they get a lot of torque because the pistons are huge. Okay, so you get torque from how big the pistons are. The bigger the pistons, the more pressure there is, right? So it pushes down, you get more torque. So when you're driving like a Cummins, right, 6 in a row, make it go. Well, they're big, right? Each one of those 6 pistons is huge, right? And that's, so you even look like a big semi truck. They don't necessarily have a lot of cylinders, they just have really big pistons. Okay? But the bigger the piston, the lower your red line. You can't make them move up and down as quickly as smaller ones. So like high-end sports cars can have lots of small cylinders. Right? So if you have like the Bugatti, it's like a W. Right? It's got a lot of cylinders, 16, okay? Arranged in like 2 Ws, 2 Vs, whatever it is. It's crazy. Yeah, they're small, so they can rev really high. And a lot of you probably just went, I was just Charlie Brown's teacher there for a minute. Okay. Okay, so basically, guys, what we have to get out of this is that engines still are doing one thing. They're converting one form of energy to another, and most of the time that form of energy is heat. Okay? They're converting heat, okay, into mechanical energy. Obviously, an electrical engine is not. An electrical engine is converting electrical energy directly into mechanical energy. That's more efficient than internal combustion. The problem with electrical is where do you get your electricity from? Okay, that kind of thing. They are definitely more efficient, and they deliver a lot of torque. Okay, electric motors can deliver a ton of torque immediately. All right. We don't need to answer those. Okay, so we're going to move on now from there.